Hey folks, in this next video we're going to talk about resistance. So at the beginning of this chapter we talked about electric current, which is the flow of electrons through a conductor. Um, so like electrons flowing through copper, let's say. Well, electrons don't flow through copper for free. They in a copper, like let's say you have, let's say here's your a cylinder of copper. It's like a copper wire or something, thick copper wire, and you hook this up to a battery like so. Okay, so remember the battery. This is the negative and positive side of the battery. So electrons, okay, will flow this way in this circuit, and then they'll flow this way through that copper conductor. Well, when the electrons are flowing through here, the copper has atoms. It's got a structure, and those electrons will bump into the atoms as they go. So it's kind of like a ping pong ball trying to get through something that has a bunch of resistance to it, or a bunch of things in the way. Or it's kind of like imagine you are trying to run through a classroom right now. Well, all the other students are sitting at their desk while you're trying to run through, and so they're in the way. So you'll eventually get from one end of the room to the other, but you're going to have to move around some, and it's going to take some time. So that's kind of like the idea of resistance. Okay. Now, what? How do we calculate resistance? How much something resists? Okay. So it turns out it depends on a couple things. So the resistance depends first on the kind of material you have. Okay. So the letter for resistance is a surprise, surprise, a capital R. Okay. And the units for this are called ohms. Okay. And the shortcut for that is we use a Greek omega. So it's like kind of like a horseshoe. All right. So resistance is measured in ohms. And that resistance depends on something called resistivity, and that's a little row. And resistivity, it depends on the type of material. So, like in your book, you have a chart of resistivities. And so, for instance, copper has a resistivity of 1.7 times 10 to the negative eighth. Iron has a resistivity of 10 times 10 to the negative eighth. So iron has a lot more resistance than copper, meaning that it's harder for electrons to travel through iron than it is through copper. Okay. Now, the units for resistivity, I'm going to give that to you in a second. It was in that chart if you looked at it, but I'm not going to give it to you because I'm going to get the rest of the equation first. Now, the next part of this is what else does resistance depend on? Well, it depends on the shape of whatever's resisting, whatever the electrons are flowing through. Now, if you had something that was this long versus something that was this long, which would it be harder for electrons to get through? Well, hopefully, if you look at that, it's going to be harder for the electrons to get through the second one because there's more stuff in the way, right? You have to travel through twice as much stuff. It would be like if I made a classroom twice as long and put, twice as many students in the way and instead go through it. It would be hard to do. So the longer something is, the harder it is to get through, the more resistance it has. Finally, what about the following? Let's say I give you two things to go through. There's number one, and there's number two. Okay. And I said you have to go from one end to the other. Which would be harder to get through, A or B? Okay. Well, initially you might think B, but it turns out that A would actually be hard to get through. Now, here's my analogy. Imagine you are drinking a milkshake. All right. Now, if we go back up to the top here, these two guys, the longer the straw you stick in the milkshake, the harder it's going to be to get the milkshake out, right? If you have a straw that's 5 feet long and you try to get the milkshake out, it's going to be really, really hard, right? Well, now look at these two guys right here. All right. If those are my two straws, which one would be harder to get the milkshake out? Well, the top one, right? The bottom one's fatter and it'd be easier to get your milkshake out. You're more likely to get that brain freeze, right? So what we're talking about here is this cross-sectional area. So we're going to call that A for area. So it turns out if you put all this together, resistance is equal to that resistivity, that depends on the material, times the length of the resistor, divided by that cross-sectional area of the resistor. Okay. Now, area is measured in meters squared, length is measured in meters, resistance is measured in ohms. So what does resistivity need to be measured in? Well, it needs to be measured in ohm meters to make everything, all the units work. And if you look at your chart up there, it says ohms times meters. So there you go. Okay. So that's the equation for resistance. Now, some kind of questions we'll ask you. We'll ask you a couple plug-in chugs. Just, you'll plug in these and get a number. Make sure your area is in meters squared. Make sure your length is in meters when you do that. But more conceptual type questions are the following. Let's say I've got a resistor that's fairly pliable. And let's say I stretch it out. Actually, better yet, I lied. Let's say I have that, and it's got a length L. Okay. And let's say I add 2 more to it like so. So now the total length is 3L. By what factor does my resistance change? Well, I didn't change rho. I'm not changing this cross-sectional area, but I am making L 3 times bigger, so the resistance would be 3 times bigger. Okay. Now, conversely, what if I took this resistor and now let's stretch it out? So we're going to stretch it until it's 3 times as long. By what factor will the resistance change? Well, the answer ain't going to be 3 this time. Okay, you're not adding material to make it 3 times as long. You are stretching this thing. As you stretch it, it's going to get skinnier, right? It's like Play-Doh. If you stretch Play-Doh, as you stretch it, it gets skinnier, okay? So by what factor is the resistance going to change? Well, here's what I do know. The amount of stuff in this example isn't going to change. I have the same amount of stuff. So the volume isn't going to change. Well, volume equals area times length. This would be your area. This would be your length. Okay. We're making the length 3 times as big, but we're not changing the volume, which means the cross-sectional area has to become 1/3 of what it was. So that's why it looks skinnier. Okay. So now if we look at our resistance equation, okay, you didn't change rho. You made this 3 times bigger, and you made this 1/3 as much. What's 3 over 1/3? 9 times. So if you stretch this out to 3 times its length, it'll have 9 times the resistance it had before. Okay. Now, finally, you might have irregular shapes where you can't, where A changes over the course of the length. So, for instance, what if I had, this shape? And I said, find the resistance of that. Okay. Well, you can't just use A because A changes as you go through the shape. So here's the example I'm going to do. Let's say you had the following. Let's say you had a sphere that was hollowed out like so. And so this is your material right here. Okay. And we were sending electrons from the inner to the outer surface. So we hook up our battery so that the battery starts there and goes there from A to B. And by the way, those will be the 2 radii we're going to talk about, radius A and radius B. All right, so how do you calculate that resistance? So what you do now is you integrate. So you get the integral of rho over A times dl. Okay, now in this case, so imagine we're looking right there. Okay, so if we make our resistor skinny enough, A is not going to change. So in this case, our resistance would be the integral of rho, whatever kind of material that is. If I draw this all the way around, what area is that? Well, that's 4 pi r squared. And then dl is actually, it becomes dr. We're looking at the difference from the beginning of this thing to the end of that thing. So if we had a very skinny resistor, its area is just 4 pi r squared, right? That doesn't change much when you go from the inner to the outer part. So what we're going to do is we're going to take one skinny resistor and then we're going to pile on concentric ones and add up all their resistances. That's what you do when you integrate, is you're adding, and that will give us the overall resistance. Now, our resistor starts at A and ends at B, so those are your 2 limits. Okay, so your resistance will then be, well, you can factor the rho and the 4 pi out because those are constants, And what are you integrating? You're integrating dr over r squared from a to b, which is the same thing as integrating r to the negative 2 dr. Okay, so what do you get when you do that? Okay, so the rho and the 4 pi are constants. And if you integrate r to the negative 2, it becomes r to the negative 1 over negative 1. And you have to evaluate that from a to b. So this becomes rho over 4 pi. Negative 1 over r to the negative 1 is negative 1 over r. And I have to evaluate that from a to b. And if you do that, you get the rho over 4 pi, and you would end up with 1 over a minus 1 over b, if you're careful with your negatives and such. So that would be the resistance of this shape right here, going from the inner to the outer surface. And you can do this kind of thing with any regular shape that you're able to make into a concentric things or adding on things. You would do a similar process on this. It depends on if it's rectangular or circular, how you would do it, but it'd be the same idea. So this, generally speaking, when you try to send electrons through something, there's going to be some stuff in the way. That's resistance. That resistance depends on the material. That's resistivity. That's your little rho. And then the geometry of the resistor. How long is it, and how thick is it, or how much area do you have to go through? So I hope that was helpful, and thank you very much.